Recording in progress.
To my second talk. And today I want to present a different aspect of my work, a different line that I also started during my first postdoc at ICTP in Trieste. And this is about this idea of entanglement Hamiltonian. Okay. And if I have time, I also want to discuss a bit about something that I started to discuss yesterday, that is about unsupervised learning, but focus in the quantum aspect, the quantum criticality. Okay, so just as an introduction, so as I said yesterday, like my main interest is in studying like lattice models. So something like this. Okay, and more specifically, like spin models, spin Hamiltonians. And here I want to focus everything that I will talk here. It's about local Hamiltonians. So basically, the interaction between the spins are like local, are nearest neighbor, or like yes. In the case that I will talk here is everything nearest neighbor. And more so, just another aspect for the introduction is that here I will focus on ground state properties. So everything that I will discuss here, it concerns like ground states of this local Hamiltonian. And so before start talking about this entanglement Hamiltonian and why we want to study this entanglement Hamiltonian, let me just introduce some concepts about many body entanglement. So basically, I'm interested in studying the entanglement between two complementary parts of a system, A and B. And this system is described by a pure state. Okay, it's the ground state. Okay, so basically the idea is that.
Sorry, Tiago, are you using a pen or something? It's very hard to read.
Okay, let me try to. Yeah, my letter is not so good. I will try to do my best to improve.
It's really very hard to read this.
Okay. Yeah, I'll do my best to improve. So basically, the idea is that I think you can write here. Yeah, my pen is not so good. Let me. Yeah, so basically, the idea is that we have entanglement when you cannot write the state, the pure state, as a separable state. And the main quantity of interest when you talk about entanglement are like entanglement measures, that is like entanglement entropies. And I think now it's a bit better. And so the basic quantity that we need to let's say to measure or to compute in order to access these entanglement entropies is the reduced density matrix. Okay, that is defined as the partial trace of the state. Okay, and here more specifically, you are interested in the von Neumann entropy, in the Renyi entropies. Okay, that is defined as the right. Okay, so this is the definition of the von Neumann entropy. And one aspect that I want to focus here is that how to access this kind of quantity in many body system, more specific in lattice models. Okay, so basically this is typically a very hard quantity to access. So for example, you cannot access this quantity in quantum Monte Carlo simulations, for example. Okay? And the reason is that here you have like the expectation, is like we have expectation values of a nonlinear operator, right? It's the log of the reduced density matrix. And also in experiments, in order to measure this quantity, in principle, one would have to measure the reduced density matrix. Right? So there are other quantities that entanglement entropies that we can define, that is called Renyi entropies. That is defined, sorry, it's the other way around. is defined as the log of the trace of whole way, right? I hope you can read this. Okay, so this Renyi entropy.
It's quite hard to read. It's okay because the formulas are well known, and so we can guess what is there. But as you will move to new stuff, it will be challenging to read the formulas that cannot guess what they are.
Yeah, I think the problem is my pen.
I don't think this is not. I don't think this is working.
Do you have another pen or what?
Yeah, I don't. Yeah, what I can do is I can open. I have another presentation that's already prepared, so maybe it's better if you.
Okay.
If it's fine for you, I can do this.
I mean, isn't there a blackboard there you can use?
No, I'm at home. Yeah. So the other presentation, I think I use it.
But is it the same material? The other presentation?
I think it's the same. Yeah. Let me.
Okay.
Can't you type in the computer?
No, that's.
No.
Or the equations is bad.
Let's see if it's better like that. Is better?
This can be good at least.
Yeah, this is better.
Okay.
Still a little. Okay.
Yeah, sorry. I'm not. Yeah, I think the problem is the pen that I'm using, and also I'm not so used to write. Okay. Okay. Let's see if, in the worst of the case, I try to type.
Okay.
All right. So yeah, basically, so this is what I just said. Okay. So just definitions. Okay. So basically, I'm interested in like trying to access this kind of quantities in many body systems. As I said, that in principle, typically it's very hard to measure these quantities. So yeah, so just one what I just said, and here what you focus is in this concept of entanglement Hamiltonian. So basically, you consider a case in which I can write the reduced density matrix of the system as an exponential of an operator, right? And this operator we call entanglement Hamiltonian, okay, or EH, okay, we call EH. And the basic idea is that the entanglement entropy can be defined as thermodynamic properties of this operator, this entanglement Hamiltonian. So in principle, if you know this operator, we can access entanglement measures by performing like thermodynamic measures, okay, that we can do with Monte Carlo, for example. Okay. But the question is that we don't know this operator, right? So giving a model, let's say, let's define this way. The question is, how is this entanglement Hamiltonian of a certain subsystem, okay? So here you will consider the simplest case that the subsystems are like connected, okay? And in principle, this operator can be very different from the local Hamiltonian that you have of your original system. It can be a non-local operator, okay? It can be a very complicated operator. All right, so
you're looking at ground states only.
Ground states, yeah, of local Hamiltonians, yeah. So what I will do is that I won't compute this entanglement Hamiltonian. Okay, so my strategy is to, so I will discuss some results that is known in the literature about this entanglement Hamiltonian, both for lattice models and for quantum field theories. And then I will use as an inspiration some results of field theories, more specifically the lattice discretization of these results to establish an ansatz for this entanglement Hamiltonian. Okay? And then I will try to do some numerics on these. I will show some numerics on these, let's say, ansatz for the entanglement Hamiltonian. Okay. All right, so the first case that I want, so now I want to discuss about lattice, entanglement Hamiltonian for lattice models. Okay, so one case that we can compute this entanglement Hamiltonian, even analytically, there are some results to in certain case, like for 1D systems, like the case that I will study here, but also numerically, it's not so difficult to compute this entanglement Hamiltonian for free fermions. Okay, so here's just a type binding model. Okay, so we can diagonalize this system easily. Okay. So let me discuss a bit how is the like given a 1D system like this one that I'm showing here. So here is this line here. So this is my 1D system. Okay. So the question is, how is the entanglement Hamiltonian of this subsystem? And one aspect is that so the ground state of this operator is a Slater determinant, okay, or is a Gaussian state. And for this case, the entanglement Hamiltonian, so this is the first aspect that I want to stress. The entanglement Hamiltonian for Gaussian state, the entanglement Hamiltonian is also quadratic. Okay, it has the same, it's quadratic, but in principle, can have different terms from the original Hamiltonian. This is what I want to discuss now. So in this case, more specifically, in the case that I have 1D system, and my original system has nearest neighbor hopping. So the basic idea is that one can show that the entanglement Hamiltonian has like nearest neighbor hoppings and hopping to the third neighbor, okay, and so on. So it has longer range hoppings. So the first thing is that, but the nearest neighbor is a dominant hopping, so it's much larger than the other ones. Okay. And the other aspect is that these hoppings, the T1 depends on the position. Okay, so it's not as a non-homogeneous hopping. Okay, let me try to erase this. Okay, and more specifically for this geometry that I draw here, the first nearest neighbor hopping is like it looks like a parabola. Okay, so so the hopping increase near the boundary and then has a maximum.
This is an open system or closed?
No. In principle, so here we are assuming that the whole system is infinite, just for simplicity. So,
sorry, then I'm a bit confused. So, what is the beginning and end of the parabola if it's infinite?
Yeah. So let me draw here. So I'm talking now about the subsystem, not the whole system. So.
Okay. Sorry.
So the parabola starts on the boundary.
Sure. Yeah.
So it's something like this. Okay. So yeah, this is the idea. So then we can write the Hamiltonian, so we have the first nearest neighbor hopping and the third one, and so on. So it's a longer range. So it's different from the original system. So in principle, we can even approximate this entanglement Hamiltonian, excluding the other hoppings. Like, you still have good results, as you see, as I will show later. Okay, so but this is one simple case that one can.
Sorry, to do that, don't you need to assume that the original problem has an energy gap?
No. Why?
Because I thought that essentially this is formula that Pesha derived, right?
Yeah, exactly.
You see
exactly
what these matrix elements are for the entanglement problem. And that's determined by the equal time propagator of the original problem. And if you don't have a gap, it has a power law form.
Mm-hmm.
And so you cannot really truncate this. The power law is important.
Mm-hmm. Yeah. So
that actually knows about the long distance behavior of the systems.
No, yeah, so yeah, exactly. So here we have this long, let's say long distance hoppings, like T3.
So for instance, will you get the usual formula for the entanglement entropy, which is logarithmic in the size, if you truncate to the first few terms? I don't think so.
You get. I will show results of this exactly, because what you do is exactly that. So our ansatz, it's just consider the first part, okay, the T1. But you are right. So we have so the entanglement Hamiltonian here. It's has these long range terms. So if the subsystem is larger, so you have even larger hoppings. But the point is that so numerically, the T1, I think it's more. If I'm not wrong, is like 20 times or something like that. It's larger than T3. Okay. So this exactly. So I didn't mention, but it's so this result is based on a paper of Eisler and Peschel. And I think it's a paper of 2017. I don't remember exactly which journal was. But yeah, so in principle, these results can also be obtained numerically, but in this paper, they show some analytical results. they have some analytic results. All right. Okay, so yeah, this is the idea. So the Entanglement Hamiltonian, it's different from the original one, but yeah, but the dominant term is still the first one, the nearest neighbor, as the original Hamiltonian. Okay. All right, so now maybe it's a bit confusing, but I will try to follow this. So basically, there are other results in the context of lattice models, like no results. Like, for example, for the 1D quantizing model, away from the critical point, there are some results. I think it's using this method of corner transfer matrix. So in this case, the Entanglement Hamiltonian that one obtain has the same local terms of the original Hamiltonian, okay? But with couplings that are inhomogeneous. Okay, so I won't write here, but there are. And also another thing that I want to mention, there are also results in the context of field theories. Okay, so I won't enter into the details of these results. In fact, I'm not an expert on this, but let me mention this. This is important for us because we use these results as, let's say, as an insight to derive these answers. But there are some results on the context of Lorentz invariant quantum field theories. More specifically, this is called the Bisonyanovich Theorem. And these results establish that your Entanglement Hamiltonian of the vacuum of your theory is local and has the same couplings of, so basically, let me try to write. X1. Hope you can see. But, so H is like the energy density. And X1, so basically we have your infinite system, and X1 is the distance from the boundary. Okay. All right. But anyway, I will explain this result in the context of, let's say, lattice models. Okay. So what you try to do is, we try to do in this work was to establish an answer based on this the lattice the discretization of this result. Okay. So let me try to explain this these answers. So the basic idea is that so imagine that you have your original system. So your original system, again, it's you have this nearest neighbor coupling that can be a nearest neighbor interaction. And then we want to know the Entanglement Hamiltonian of the subsystem A, okay, that is the other half of the system. Okay, so I divided the system into halves. And the basic idea is that you assume that this Entanglement Hamiltonian, the Entanglement Hamiltonian of this system, is given by an Hamiltonian that has the same local terms of the original system, okay, but with these couplings that depends on the position, these inhomogeneous couplings here. And more specifically, based on this, motivated by this Bisonyanovich result, we assume that in the case that you have this kind of geometry, like two halves, that I divided my system into halves, these couplings increase linearly as I go away from the boundary. Right. So this is the basic idea of the things that I want to discuss. So this is actually the main point. All right, maybe.
Sorry, I missed. What? Sorry, the ansatz is that the other terms you can ignore. Is that what you mean by the ansatz? I mean, there certainly are other terms. You're just ignoring them. Is that
exactly? Yeah.
Okay.
In principle, can be other terms. Yeah.
Okay.
And also, in principle, can be also let's say multi-body operators even. Okay. So, but this is really we really have to check that, right? And this is what I think the goal of this talk is really try to show some numerical results indicating that this is a good result for a broad class of ground states. Okay, this is I think the main goal here. But you are right.
Sorry, can I ask a naive question? So I guess the quantum theory result is probably derived by just thinking of evolving the state with some boost generator, right?
Exactly.
Okay, and then you evolve it with a boost generator to compute the density matrix.
Yeah.
And now you mimic that boost generator in the discrete by replacing distances by some integer n and so on.
Exactly.
if you know that your lattice description is indeed flowing to the continuum because you already studied other quantities,
Exactly.
aren't you guaranteed that it's going to work? Why is this an interesting thing to test?
I mean, in principle, you have, so here, as you said, so actually there is a 2π here that I forgot that is related to the thing that you mentioned. So basically this works for Lorentz invariant. So there are like, I mean, it's interesting because if it works, it's great, right? Because we can, as I will show you, we can compute the von Neumann entropy with quantum Monte Carlo, okay? So if it works, it's great. So it's not trivial, it's the other way around. I think it's a method to, but I think it's not trivial, right? So lattice, so your dispersion relation, it's nonlinear at certain energy scales, right? So you have like an effective field theory. You can have an effective field theory that is Lorentz invariant for certain phases, but it's depending on the regime that you are. Maybe you can have like nonlinear.
Maybe let me ask differently. Are we interested in the continuum limit, or are we interested in?
No, we are just interested in lattice models. Okay, so this is
okay. So the field theory is just to give us some intuition about
exactly.
why do we expect some modulation in the lattice and so on. Then we make a field theory inspired ansatz and we fix these modulations.
Yeah, exactly.
Okay, thank you.
Yeah. All right. So this is the. So let me try to draw, let's say, a physical picture of these ansatz. Okay. So basically, the idea is that you can think, you know, your ansatz as a thermostat. Right? So of course, everything here that I'm talking is t equals 0. So the whole system is the vacuum, is the ground state, right? But I can think in that my system is a thermal state, right? More specifically, if I put a constant of normalization here, I think it's easier to see that. But this thermal state has a temperature that varies depending on the position that you are, the distance that you are from the boundary. Okay, so this distance here, the boundary here. So more specifically, your thermostat looks warm, looks high temperature if you are close to the boundary, but very far from the boundary, it's like cold, because basically you have like a beta that it's large. Okay, so this is like a physical picture for these ansatz. Yeah. So this is so this was the let's say. Yeah, so then what we did was really to try to answer this question. So the reduced density matrix that you obtain with these ansatz is equal to the exact one. Okay? And you try to answer this question for different kind of models, lattice models. So here it's a bit disorganized, but more specifically for different kind of phases.
Sorry, can you just say a few words a bit distinguishing gapped and non-gapped? Because it seems to be quite important, right? If it's gapped or non-gapped. But
yeah, so this is,
in your presentation, you are not making a big distinction between the two.
No, but I will start now. So everything now was general, but now I will start to talk about specific cases. Okay. And yeah, so as I said, we study different cases trying to answer this question. Okay. So like, for example, critical systems in 1D and in 2D as well. Okay. Like 2D ordered phases, like antiferromagnetic ordered phases, and also, as you mentioned, gapped phases. Okay. So this is basically the three classes of the system that we study. And basically, we try to probe if this approach works numerically, because everything here you have for lattice models, for the kind of models that we consider is like an interacting model, you have to do numerically. So we probe different quantities, like let's say expectation values of local observables, okay, like A here, like given by this ansatz and given by the exact result, and then you compare these. Also, the entanglement spectrum we can compare from the exact Entanglement Hamiltonian and the one that will be obtained with the ansatz. And I think that the main let me try to add. I want to try to add one page. Insert page. Yeah. Again, so. Yeah, so I mean, I won't show the results. Of course, it will be difficult to draw here, but I think the main conclusion that we obtain with this set of numerical study of these phases here, like 1D critical phases, 2D critical phases, 2D ordered phases, like antiferromagnetic ordered phases, and also gapped phases, I think was exactly what someone mentioned, is that for a system that that is, let's say, that lose the correlation length is much larger than the lattice parameter. So this works very well, okay? Especially for this system here that we study. Like for gapped system, we start to see deviations when like for example, let me be more specific. We study like the XXZ chain. Okay, so basically the XXZ chain. So we have this delta, and for delta smaller than the 1, is delta critical. You have like a critical phase, and here you have like an antiferromagnetic phase.
Or let me try to see if I'm understanding correctly. So there are two examples we could study analytically. One is the free fermion, that even though we could do it either in the continuum or in the lattice, and we see some modulation and this linear slope close to the edge and so on. And the other example is continuum field, Lorentz invariant field theories. And there we have this boost argument to write that. So based on these two examples, so these are two simple examples where we can do analytics. One is Gaussian and the other is Lorentz invariant field theory. And then you have this Monte Carlo, which compared to analytics is a huge amount of work. And but there should be some analytic intuition about which cases should work and which should not. It should not be a mystery. You should not have to wait for the Monte Carlo results. You should have some intuition of which one should work. Can you give us some intuition?
Yeah, so our initial intuition is, I think, exactly what you mentioned, as like, so like lattice models that have like low energy description that is given by a Lorentz invariant quantum field theory. Like, for example, the critical phase of the XXZ chain. So it's described by this Lüttigen liquid. That's the Lorentz invariant theory. So this is an example of case that this works. And I will show like one result, like in which sense it works. Also, antiferromagnetic phase. It's an ordered phase in 2D. Like, so this.
But let me understand what you mean by works. If I have a critical system. Does it mean, I mean, because what I'm confused is that what you, if the wave function was given by this very simple exponential.
One application of this is exactly what you mentioned now, is that you can compute entanglement entropies. And one thing that you can do is like for this system that I said works, we can extract the universal quantities, okay? So this is one aspect. We can extract it, for example, for critical system, we can extract the central charge. And I will show the results, I hope I can. But here the results, and I will
But if your density matrix, if you can extract, maybe again, it's not something I work on, but if you can extract a density matrix, then can't you compute correlation functions?
You can also compute correlation functions, and you did that exactly. So
and you would get the correct critical exponents with such simple ansatz for the wave function, just an exponential of the Hamiltonian of the lattice. I find that very surprising. Is that true?
Yeah. So this So one thing that you computed, for example, is the magnetization, and the magnetization. It's of course there is not equal to the exact results. I would have to show here. So let me show the results like a few minutes of the entropies, and maybe we'll give you more.
But let me understand conceptually, because one thing is, of course, you do numerics, so there is a measure and so on. But conceptually, should I expect that this should give me the, if I had infinite computer time or whatever, should I expect this method to give me the right exponents of some non-trivial CFT if the lattice flows to that CFT? I doubt. It sounds too good to be true. Is it true?
Yeah, so what I show is that we can access like universal quantities from the Renyi entropy. Okay. So this is an example, I think, of a universal quantity.
I have an
critical exponents.
Let him show his results, and then we can ask him questions about his results.
Critical exponents, we didn't try actually, but it would be a good thing to try. Yeah. So yeah, as you said, like let's say lattice model that has low energy, that can be described well by low energy degrees of freedom. It works well, and we show in which sense it works well, like soon, very soon. But lattice models that don't have a Lorentz invariant, low energy discrepant, this doesn't work at all. Like one example is like the ferromagnetic state. Okay. So of the Heisenberg model, for example, doesn't work. Okay. Yeah. So these we explored like in details exhaustively in a paper, a PRB paper that we published in 2018. But what I wanted to focus here is more like in a more recent paper. It was published, I think, last year, that we explored exactly this thing. So yeah, maybe now let me try to, like, this is the initial motivation that we had. Like, so basically we cannot compute this quantity with quantum Monte Carlo. But now if you have this Entanglement Hamiltonian, the idea is that it's easy to show that the von Neumann entropy is equal to the thermal entropy of this operator. So the idea is that instead of simulating the original system, I simulate directly this Entanglement Hamiltonian in my quantum Monte Carlo.
But you need to know the Entanglement Hamiltonian now.
Yeah, but I'm using the ansatz, right? So the ansatz, it's
how do you know the ansatz is good?
Yeah, so I'm assuming that the ansatz works.
So what's the criteria?
Yeah, the criteria is the thing that I was discussing before. Okay, that again.
Okay, how do you know that for the problem you started with, you are actually doing a good job with your ansatz?
Yeah, so the conclusion
you change the problem in a sense, right?
Yeah, the conclusion that we arrived is that like models that has like an effective theory, that quantum field theory that has Lorentz invariance, this ansatz works well. Okay, so this is based on our results that you have. This is our conclusion. For other case, you cannot, but for other case, you cannot exclude that doesn't work.
Okay, so going back to the result, to this result for free fermions, where this began exactly. There is this paper, as you said, by Eisler and Peschel, where they expressed the entanglement Hamiltonian in terms of the equal time two-point function of the Fermi.
Yeah.
Okay, in a system which is critical because it's gapless, that has a power law form. And that power law is essential to get the correct, the conformal limit. So I don't know, how can you get that from the nearest neighbor?
Yeah, so let me mention, I think, one result of this paper. So in this paper, they also discuss about this this three-diagonal matrix that they call T matrix, right? And this T matrix is exactly this entanglement Hamiltonian that we are talking about here. And one thing that they show in this paper is that not in this, I think, but in other papers, that they show that the entropy that you get from this T matrix, that exactly the entanglement Hamiltonian that we have here, is asymptotically exact, okay, as you increase the system size. So you can extract the central charge. Okay.
I see. So they show that already.
They show, yeah. This T matrix commutes with the exact entanglement Hamiltonian, and the T matrix is exactly what I'm discussing here in their context. Yeah. So basically, this is what we did. So basically, for example, for the 1D Heisenberg model, so this is an interacting model. The entanglement Hamiltonian is given by this expression here. Okay. So he asked one important aspect here that comes from the discretization of let's say this Bisonyanovich result is that we have to consider a prefactor here, and this prefactor is fundamental. Okay? This is like an overall energy scale, and this is related to the velocity of the. So we need to know this velocity to put here. Okay, and for the Heisenberg model, we know. Okay, so here are the results. Okay, so here I show in blue is.
May I ask a question? Sorry. So what is the Hamiltonian that you're writing there? This. Is it an Ising without magnetic field, or what is it?
Yeah, it's a Heisenberg model.
Oh, it's a Heisenberg. Oh, I see. Okay, thanks.
Maybe it helps. Yeah. It's a quantum Heisenberg. And here so the geometry that I'm considering here is like I have a 1D chain, and I split this 1D chain into 2 equal halves. Okay? So basically here, let me try to discuss a bit these results. This is so in blue I have exact results. So this is computed by exact diagonalization, and the red and the blue are results obtained by the Entanglement Hamiltonian. So here we have 2 kinds of Entanglement Hamiltonian. The first one is this black points, okay? And the black point is exactly this Entanglement Hamiltonian here, N. Okay? So, but this is for an infinite system, okay? So it's let's say the quantum field theory result in principle assume an infinite system. Okay, so for that reason, you have this shift here. Okay, but it turns out that there are some generalizations of this Bisonyanovich result that I mentioned here. For CFT systems, there are some generalizations of these results. Sorry for my mess. Okay, there are some generalization of the results that consider other kinds of geometry. Okay, so these are a paper by Eric Tony and John Carney. And they consider finite systems. Okay? So then what changed is that now we don't have this n anymore, but you have another function. Okay? So now, okay. So basically, I don't remember the exact formula for this function, but it's given by their theory. So there is an exact expression there. You can plug in here. And this red results is exactly this. Consider that. So when you consider that, we match with the exact results. Because the exact results, of course, it's for a finite system. So, but the point is that you can extract the central charge. So this is the main point, right? So you can extract. So we also consider other case. So this is just one example. We also consider the Ising, the quantizing model at the critical point. And then we show that we can extract the right central charge. Also 3-state spots model. Okay? So different examples of model. Right. So this, in which sense this works. So this is one example. Like for free fermions, we can even do like very, let's say, huge system size, because then it's easier to do numerics. And then we can really, one thing that we see is that if you compute, so this is for free fermions, if you compute the difference of entropy between the, let's say, the exact, and there's one that will be done with the, so this difference that will be done with the ansatz, this difference, one thing that we show that goes to 0 in the thermodynamic limit. So this we show numerically, okay? So, and here, but here, like, so for example, here, like the difference between blue and red, there is a difference, it's not exact, but the difference is very small. So in this scale, you cannot really see. Okay? I think for this point, it is less than 1%. Okay? Put this in the paper. So in that sense, it's a very good approximation, right? Okay, so but in principle, so this is a 1D system. And one point is that in terms of numerics, let's say tensor networks works very well to compute these quantities for 1D systems. But the idea is that we can use this as a method, because in principle, this works for higher dimensions as well, right? As long as these requirements that I mentioned before is valid, it works. So you can extend that for 2D systems, okay? And in fact, we did that. So this is really quantum Monte Carlo results. And we compute so this is the thermal entropy, again, of this, let's say, the generalization of these ansatz for the Entanglement Hamiltonian for 2D systems. Okay? So now we have something like this. So B and A. Okay? So now basically the distance from the boundary now is this boundary here. Okay? And here is like your system has periodic boundary condition. Oops, so this is, okay. So these are the results for so these are systems that breaks a continuous symmetry, okay? So these are an unferromagnetic state. So HM here is the Heisenberg model, and XY is the XY model, okay? So the ground state of these models, they break continuous symmetry. Okay? So they are characterized by spin waves, by Goldstone modes, right? Goldstone modes. And one interesting thing about the scaling, so here I'm really probing the scaling of entropy. Okay, let me show what I'm doing here more. Maybe it's a bit confusing due to this. Let me, of course, the geometry that I will draw is not the exact one, but just to illustrate. But what I'm doing is really probing like how the entropy change scales with the size of A. Okay, and what we have here is that, so in this case, we have that the first term is a linear term in L. Okay, that is an area law term. It's called an area law. Here you also have a constant called delta. But here you also have corrections. So we have, for example, logarithmic corrections. And also some other things. Okay. I don't remember exactly. I think there is a 2 here, if I'm not wrong. Yeah. And there are some quantum field theories that predict this scaling for a system that breaks a continuous symmetry. Okay, for an ordered system that breaks a continuous symmetry. Okay, and this NB here is related to the number of Goldstone modes of the excitations. Okay, so and then you can compare these the numbers that you get with the expectation. So for the Heisenberg, we get
so is related or is equal to the number of Goldstone modes?
Is equal. Sorry, is equal. Yeah, is equal. Yeah, I said the prefactor is related because there is another thing here. I think it's divided by 2, if I'm not mistaken. Was times 2. Yeah, I think, yeah. So it's exactly what I wrote, if I'm not mistaken. But the point is that for Heisenberg, you have NB is equal to 2. So this number of Goldstone modes is equal to 2. And for the XY is equal to 1. Okay, so we can, and the results that you get is is an agreement with that. Okay. So B here is this prefactor here, right? So the idea is that we can extract these Goldstone modes. Okay. So I think what is interesting about that is that we can really use this in terms of numerics, that we can really use to like conventional Monte Carlo to compute von Neumann entropy, as long as this ansatz works in the sense that I tried to describe it before.
So just to, I mean, I think this, to summarize all the questions, I mean, the ansatz is an approximation. It's not an ansatz. Yeah. And the question is, is the approximation valid? And that I think is, you still leave it open. You don't tell us when it's valid and how, what's the error bar in the approximation?
Mm-hmm. It depends the quantity that you are measuring.
In other words, what are the corrections to that? If I actually were to work with the full entanglement Hamiltonian.
Corrections in the entropy, you mean?
Yeah, suppose I use the full entanglement Hamiltonian that in principle you can compute.
Mm-hmm.
It's a complicated expression. Non-local.
Yeah.
So in fact, the spectrum is has a complicated spectrum generally. It's only the low-lying modes that have some simplicity.
Yeah.
Okay, so the question, that's why I was surprised that you could do this with only the nearest neighbor form, because only the low-lying part of the low wavelength modes, if you wish, in particular here, that are actually word captured, are universal. The other ones are not.
Yeah.
So there is a question, what are the corrections? If you make your approximation, which is rather drastic, and suppose you want to look at the effect of the tails or the next nearest neighbor terms, they may be small, but if they are singular, can be big. If they are singular. So there is a question of the goodness of the approximation.
Yeah. Yeah, of course, this is difficult to be addressed numerically because we need to study case by case, but yeah. Yeah, I think there is so there is one work that you really study extensively, like a comparison of Rayleigh entropies between the exact and not co-answer, this PW result. This is for 1D critical system, and here there is this aspect that you really see that. So basically, for the 1D critical system, so the leading term is this. This term here, right? This divergence, the logarithmic divergence. But you also have other terms that also has universal properties, right? Subleading terms, okay, for this kind of system. And we check in this paper that I mentioned. So it's so I'm first author. I think it's a PRB 2019. We checked that even the subleading terms of the von Neumann entropy can be captured by this approximation. Okay? So in fact, yeah, as I mentioned, ds goes to 0 for like the system that you can study for numeric from high, very close to the thermodynamic limit. We show this. Oops. Okay. Yeah. So I think this is the message. Yeah, I think the message that for like system that whose low energy degrees of freedom can be well described by a Lorentz invariance theory, we can at least access the universal quantities related to the scaling of the entropy, the von Neumann entropy. Okay? So I think this is the main result of this discussion. Yeah. So in principle, you can. The idea is that I want to try to extend that for other system. That is so. The point now is that we have a tool that numerical tool that you can probe this scaling of probing area law, for example. Okay. All right. So yeah. So this part I finish. So I have a few minutes yet, 10 minutes. So maybe, yeah. Let me see what I put here. Okay. Let me discuss this aspect. Okay. So I won't enter. So now let me move to another, let's say, topic.
Sorry, just another question. You said you could probe the area law, but I thought this ansatz builds in a precise scaling. You are never going to get a scaling that is not the one of the CFT by definition, no?
But why? No, but so the example that I show is just contradicts that, right? This example just contradicts that, right? So this is not a CFT, right? This is an ordered phase. Okay.
Okay, so let me understand. So I missed something.
Yeah.
I thought you were getting the central charge.
Yeah, for this kind of for critical systems, yes, because then it's what to expect, right? All right. Okay, so now as I still have like 10 minutes, let me give you so basically, let me try to discuss about the methods that I use to compute this entropy. There are like quantum Monte Carlo methods. So basically, I wanted to briefly describe this other project that is related to use these unsupervised learning techniques that I discussed yesterday to probe quantum criticality, to probe quantum critical points, right? So basically now I have a model that has a parameter G that induces a quantum critical point. Okay? And the key idea was exactly what I discussed yesterday. So basically for classical systems, okay? Yesterday was everything classical. So basically I have my partition function, and then I sample this partition function with Monte Carlo. So I sample these configurations, X. And then the idea is to try to extract physical information from this raw data set. So this is the goal that, and we also try to do this for quantum system, more specific for quantum data sets. Okay? And basically these quantum data sets are like data sets that you have in quantum Monte Carlo. Like, so we need to do like a quantum classical mapping, and then you define these data sets. So now I will discuss a bit about the methods that I use. So I won't enter in the data mining part, but at least I will give you an idea. I hope I give you an idea of the quantum Monte Carlo that I use like in different projects, including the project that I just mentioned, like to compute the entropy, the thermal entropy. All right. So basically, the method that I use is called stochastic series expansion. So basically, there are different kinds of quantum Monte Carlo. It depends how you do this mapping, the classical quantum classical mapping. And the key point of this method is to expand the partition function, like this exponential here, in a parallel, okay, like here. So if you do this, we can insert again in the Hamiltonian, in the partition function, and also can use a complete basis. And then you have something like I wrote here. So you have like the set of, let's say, the set of matrix elements. Okay. And this is the weights of my quantum Monte Carlo. Okay. So basically these are configurations that I would like try to explain here below. And these are this whole thing in green here are the weights of these configurations. So basically these configurations can be represented by, as I'm representing here. So these red things here. So like here I have a system with 4 spins. Okay. And then like each state here, so it's a state, so it can be written as, so I have to choose a basis, then I can, so here like the full circle represents spin up and the open circle represents spin down. And these rectangles here represents the operators, okay? So it's like I have like this propagation of states. Okay? So this is one configuration. And the idea is that I can sample that with quantum Monte Carlo, with stochastic series expansion. Okay? So I have this weight here, and then I can, using, of course, I'm giving a huge jump here. I don't not telling how I'm sampling, but I'm just saying that you can define, in principle, let's put it this way, a probability, W, and then using like the Entropies algorithm to sample like configurations like this. So this is, in some sense, is equivalent to like path integral representation of the partition function. And yeah, so
Tiago, this restricts you to problems in which there is no sign problem, right?
Exactly. This is what so basically, let me see if I discuss this. Yeah, I think I discussed this a bit here. Yeah. So basically, yeah, this is the probability, and this works very well when this W is always positive. Okay. But there are interesting cases like interesting physical cases. So when this W is positive, always positive, we call that you have a sign-free problem. And then this, I would say, is the best numerical method for at least for a spin system. So basically, this works for like Heisenberg models in a bipartite lattice. Okay, Heisenberg models in a bipartite lattice, this is true. But if I put a Heisenberg model in a lattice that has some kind of frustration, this is not true anymore. So basically, there are certain configurations that this can be negative. So then I have this so-called sign problem. So this is one, in fact, this is one of the big problems of, so for example, like triangular lattice, I cannot simulate. I mean, in principle I can try, but okay, so the problem is, I just like briefly mentioned. So the problem is like expectation values of the like certain quantities. U depends on like the inverse of the variance of the sign. Okay. And the sign goes to 0 very fast. So basically, so this variance. So basically, the error bars that you have in the measures that you do, it's huge due to this problem. So you need to do like the amount of, let's say, steps that you need to do is exponentially large. So this kind of like triangular lattice is very hard to solve with, let's say, it's exponentially hard to solve with SSC.
But Tiago, so if you apply it to problems where there is no sign problem, in principle, you can take the original Hamiltonian. Can you hear me? So I'm saying that if you can only apply it to problems where there is no sign problem, then you can apply to the whole problem a Monte Carlo method directly. And with the Monte Carlo method and the replica method that you mentioned at the beginning, you could compute the two Renyi entropies as well, and extract from there all the quantities that you're extracting. So what would be the advantage in that case?
Let's see if I understood. The advantage of considering the Entanglement Hamiltonian, you mean?
Yes, because you see, you apply this method, but you have to have a Hamiltonian that doesn't have the sign problem.
Exactly.
But if you don't have the sign problem, I can take the whole problem and solve it with Monte Carlo to start with and compute Renyi entropies.
Okay, yeah. I mean, so one advantage, let me return here, is that this method is simpler than the replica trick that is used. Because here you don't need to consider this complicated topological let's say path integral that you need to use to use the replica trick to compute the Renyi entropy. So this is simpler. So in that sense, it's better than the conventional Renyi entropy method, I'd say. In the case, of course, that this works. But the Renyi entropy is exact, right? So computed with the replica trick. Yeah. But again, but this Renyi, so using this replica trick, I think that you mentioned, you just can compute Renyi entropies with n larger than 2, right? You cannot compute the von Neumann entropy.
Well, you can compute the 2, the 3, the 4, and then look for an analytical extension and then interpolate to n equal 1.
Yeah, it's true, yeah. But this, I think, will be very hard, computationally will be very hard, right? Because you have to, I think, yeah, you're right, you can do this. But I think in terms of CPU hours, you would have spent much more than doing this trick that we are discussing. Yeah.
Okay, thanks.
Yeah, so yeah, again, so yeah, at least I could discuss a bit about quantum Monte Carlo. But again, I wanted to make connections with this unsupervised learning. But I think my time is almost done. But the point is that, let me just mention this and then we conclude. The point is that we can, so now that you have these configurations that you can sample, we can define quantum data sets. It's like, so it's already defined here. You can define quantum data sets. So basically we define data sets that are like generated by single slice of my path integral, like just one slice, or data sets that is composed by a certain number of slices, like more specifically with beta slice. Okay? In our case, beta is always a multiple of L. Okay? So then you define these data sets, and then you consider like the same analysis that I discussed yesterday for the classical system, like this intrinsic dimension. We apply it for quantum system for these data sets. Oops. Yeah, I have some results here. So here are the results for the quantizing model in 1D quantizing model. And here is the 1D XXC model. So here I plot this, sorry, I won't have time to explain, but it was exactly what I explained yesterday, but I compute this intrinsic dimension, right? As a function of the transverse field. And then we see this minimum that I discussed yesterday, and also the scaling of this minimum of system size towards the critical point as we increase the size of the system. And for the XXZ, we have something similar. You also have a quantum phase transition. So you have this delta, and that when delta is equal to 1, I have a BKT phase transition. And here you also have this behavior of the intrinsic dimension. Okay, so we have a minimum, and then this minimum shifts towards this. The critical point here is equal as okay. So there is also this quantity delta R1 that you define it, and so this quantity is related to this statistics of distance in configuration space that I discussed yesterday. But again, yeah, I think with that, I finish my presentation. This is all. Thanks for everyone.
Okay, thank you. So questions, so we have time for questions.
Can I ask a question?
Yeah, of course.
Yeah, sure.
So let me understand something. So your plots are amazing when you have this 1% agreement and so on. So I just would like to understand, is the interesting, I want to understand if we should be surprised or if what is interesting is not that it works, but how you make it work. Namely, is it obvious that it has to work and therefore it's nice because it's a new tool that we can use and we know it's going to work? And that explains why the results are so good. Or are the results so good and it's a mystery? And maybe if we do other CFTs that are a little bit more complicated than desizing, the agreement will be 10%. How should I think? Is it guarantee that it's going to work and it's a new method to compute? Or it's a case by case, I have to test, and sometimes it works because the model is much simpler. But if I do a slightly more complicated CFT or critical point or gap theory, it will not work as well. How should I think of this of your method?
Yeah, I think you I would say that you should be surprised at that work. And when it works, it's very powerful, I think, because I mean, it was mentioned that it's powerful in terms of numerics. It's powerful. You think that's why?
I mean, because if I'm surprised when it works, then if I will study a new theory that I don't have an
I'm surprised that works.
What to do with the result?
Yeah, as I said, so for the entropy, there is another case that we studied. There was a critical point in 2D. And but again, it's difficult. So then we are in a regime that is difficult to benchmark because we don't have the entropy with other methods because we cannot compute the entropy with other methods. So the only thing that you can do is try to extract some universal like quantities from the scaling of the entropy and see if match with the field theory associated to that. But I don't come from, like, I'm not an expert on field theory. So for me, it's difficult, even difficult to say if it's a surprise or not to work. Okay? So in the sense that if you discretize a field theory, you always, if you discretize a field theory and in a model, and then you have this model has this, the symmetries of this field theory, there's a low end, there's like an effective description. I don't have a lot of intuition to say like when you have like errors on when you. So for me, it's difficult to say if I'm surprised or not it works. But for me, it's a very powerful tool, I think, in terms of numerics, without doubt. And I think this, already this example, it's already like a new result. Okay, so in fact, you could not even benchmark that. Maybe you can benchmark that with tensor network, but we didn't try it. But in terms of
it's hard to use a method and trust a method if we don't have a reason to expect it to work, right? If we say it's a miracle when it works, and sometimes then it's why.
But at least like the fact that surprised people, it's I feel happy about this. So, but yeah, though the point is that we need to maybe study more. That's more hard. And,
well, this result in particular that you're showing here was studied directly without using the entanglement Hamiltonian, at least for the second Renyi entropy. By Melko using quantum Monte Carlo.
Yeah, exactly. Yeah. So we can also compute the Renyi entropy using this internal Hamiltonian. It will also depends on thermodynamic relations. So, but I never compare. Actually, it's something that we could do, but we didn't. Yeah.
So sorry to insist. So let me just ask if this is true.
Pedro, Ignacio has his hand raised. Let Ignacio ask a question first.
Well, this is maybe related. I don't know if I'm interrupting or not. It's something that I miss. So is your claim that this should work for critical systems and for non-critical systems it shouldn't work, or for non-critical systems you don't know? So what is the claim? No. I have to leave for a second, so I missed. Maybe you have said that before.
Yeah. For non-critical system, I would say that a priori you cannot say anything. So there is one example that this works for non-critical system. That is the quantum Ising model in 1D. Okay? So in fact, this result of the quantum Ising model in 1D can be derived by using this corner transfer matrix, and the Hamiltonian that you get, the Entanglement Hamiltonian that you get, has exactly the same shape of this what I call ansatz. Okay, so it's surprising that sense, but in this case, it's a non-critical system. Okay,
it's not surprising since it is in disguise. It is a free fermion system.
Sorry, Eduardo, I didn't understand.
Since the one-dimensional quantum IC model is effectively a free fermion.
Yeah.
So it's not surprising.
Okay, but it's non-critical, right?
But
we know the wave function exactly in that case. Okay, so.
Okay, no, but it's non-critical, right? So if this argument of.
Well, you can use again the work by Pesha.
Okay.
Okay.
But is it true, Eduardo, that if you're not at the critical point for the Ising model, still if you build in this way this entanglement Hamiltonian, that you would get the right entropies? This is what you're saying, Tiago. No?
Yeah, I know.
Yeah, exactly. This is true.
Okay, in the continuum limits, I mean, you find that, but typically that relies also on understanding the long-range correlations that you have in the system. So I don't know if we can actually do that by keeping only the nearest neighbor part. I'm not an expert in this particular detail, and I'd like to know what the corrections are and when they are important. This is a question that was asked before.
Yeah.
I have a question on your second part, which had to do with yesterday's talk. I still don't understand what quantity your effective dimension effectively measures, and what is the criterion. I mean, you're saying that you can use that to compute critical exponents, for instance, and I think it's impressive that you can do that, but I don't know what the justification is for that.
Yeah, so
that controlled by the 2-point function. Do you need to know all of the n-point functions?
Yeah, let me try to draw here. So basically, this comes from this distance, Euclidean distance.
So this is essentially you have two configurations, and each configuration is drawn from a Boltzmann distribution, right?
Exactly.
Right?
Exactly, yeah.
And you define the distance to be what?
So this is the definition of distance. Maybe I'm losing some prefactor here. So basically my configuration, my spin configuration is a vector, right?
Yeah, so what's the logic for this definition, first of all?
Yeah, so this is so how we try to draw an argument to say that like distance are related to correlation functions. Okay? So basically this part here looks like a correlation, but it's like a correlation between two configurations, right? It's like, you have a configuration I and J.
It's looking at an overlap of two configurations in some sense.
Yeah. So we're basically like when you sample, like let's say when you sample a ferromagnetic state.
Yeah, for instance.
So you ought to have like let's say a configuration that has a huge weight, right? And this configuration, it's something like a homogeneous ferromagnetic, right? So something that all the degrees of freedom are like the same. Okay?
So this will be saying the broken symmetry state.
Yeah. But even like if you approach the transition from this, I think it's still reasonable, right? To think that this configuration it has a huge weight, right? So
no,
so basically
the approach of phase transition has a very small weight.
Yeah. Okay, but yeah, basically this is our like heuristic argument. So if you assume that, we can write like if you expand this square root, we can write these in terms of things that are like k, k and let's say k prime. Okay, and these are correlation in real space, right?
No, but this is you have k only here. I and j.
No, but if you expand the
I and j and the two sample, essentially the two configurations are labeled by I and j, and k is the location on the lattice, right?
Exactly. No, but I'm assuming already that I can like what I'm doing is that I'm assuming that I can consider this reference state, we call a reference state, that has a huge probability, at least inside the order phase. So here now becomes a constant, okay? That is, like, say, the magnetization.
Okay, so
and here you can expand, like, when this is small.
You want to know what is the distance between a given configuration from some fiducial, some reference state that you chose.
Yeah.
For example, it can be the broken symmetry state or the high temperature state.
Mm-hmm.
You can choose either, I suppose. It doesn't matter what you choose. Okay. Well, it may matter, but then you say if you do the expansion, this actually will give you all the moments.
Yeah. I'm not saying that, I'm not claiming that you prove or add that, but this is just like an risk argument. Distance are related to correlation functions.
Okay, so the condition now, okay, so this is the distance. The dimension is defined from what? How you find dimension?
So the intrinsic dimension, like, can be approximated this way. So it's the inverse of the log of, let's say, so R2 star is like a reference second nearest neighbor distance. So this is an approximation, of course.
Sorry, what is neighbor? So these are nearest neighbor points on the lattice?
No, sorry. It's in the configuration space, right? So
what do you mean by neighbors? What do you mean by neighbors in configuration space?
Yeah, so basically I have all my configurations, right?
So you have a bunch of configurations.
Exactly. So then what I do is the following. I look let's say the configuration 1, and then I compute all the distance between 1 and all the other points, okay, in this high dimensional space.
Okay.
Using exactly this formula.
Okay.
And then I just so the first neighbor is exactly the one that like has the smallest distance, right? So
you classify them by the distance to your initial configuration.
Yeah, exactly. So at the end, what we have is this empirically you can obtain like a probability distribution of distance, right?
Yes.
So what we show, another thing that we show is that like moments of this probability distribution also exhibit scaling behavior numerically. So for example, the variance of this probability distribution. So it's exactly the result that I showed before.
So is it dominated by the 2-point function?
Yeah, so this is one thing that I'm not sure, to be honest. I'm not sure, okay? So for the Ising model, in fact, what you mentioned yesterday, I was thinking about this today, and because I don't know, I'm not so sure if like correlation functions that are known to body is also critical or no, it's also singular or not. This was something that I want to check. But I don't know. The answer, I don't know if it's dominated by 2 body.
If you do this in high enough dimension, where the theory basically is mean field plus Gaussian fluctuations, there it should, for sure, should be dominated by the 2-point function.
Okay. Mm-hmm.
Okay, so, but if you approach, say, the upper critical dimension, say 4, then you will have to begin to worry about the contribution of the 4-point function, and things of that sort, and that's where the RG enters. Yeah. So there is a question about what is the systematics of this.
Mm-hmm. So if you believe in this, let's say, like, simple argument that I try to pass you, like, and expand this, square root.
This is your idea, or this is something that somebody else has proposed?
So this, I mean, was like discussions with, let's say, but I had a, let's say, a big contribution for this idea, I would say.
Okay.
Yeah. So it's basically me and Marcello, maybe that Marcello da Monte that proposed this. Okay. Yeah. Yeah, so this is something that I would say that the question that you asked me, like if which kind of correlation is dominant one, and if you can access correlation that goes beyond 2-body, like correlations, is still open, I would say. I still don't know the answer. But the results indicate that, yes, we can access multi-body correlations, because otherwise I think would not be possible to detect BKT points, right? With because if you look at just 2-body correlations to detect the BKT points is very hard, right?
Yeah.
So this is the evidence that suggests to me that, yes, we have multi-body correlations in the game. Right?
Pedro, you had another question? Did I interrupt you?
No, well, no, it's out of context now. It's okay.
So I had a question. I mean, in principle, could you use these Monte Carlo to predict properties of real materials, or is it just lattice models?
We can, yes. I mean, so for example, like for example, the highs, it depends on the material, right? And how complicated is the material? So for example, the cube rates.
Just tell me how do you get information from entanglement? How do you, if somebody gives you material, how do you?
You say concerning
what HA is, what your Hamiltonian is, what do you do?
Concerning materials, I would say I don't know, because I don't know if I think it's not possible to measure these materials, right? But in these experiments that I was mentioning,
you can't measure this in materials. What's the physical significance of these computations?
So you can measure this in these synthetic quantum systems that I described yesterday, right?
No, you can, even though you cannot look any ferromagnet, real ferromagnet done in experiment that has uniaxial anisotropy at long distances is well described by an Ising model. The question of whether you can compute microscopically the value of the exchange constant is a complicated story, but you can use.
So I have to put the charger in my computer, otherwise you turn off. So I return in 1 minute.
Yeah.
Just 1 minute.
So I guess what I'm trying to ask is, so machine learning is now being used to try to study new materials, right? To try to predict new materials. Is any of this, can you hear me?
Yeah, now I can hear it, yeah.
I guess machine learning is now being used to try to predict new materials, right? To try to predict the properties of new materials. Is this completely unrelated to that? Or is there some relation of this to what they are doing?
My impression is that the answer is not. I mean, you're using this to actually examine the behavior of model Hamiltonian.
Exactly.
Using this method. The model Hamiltonians are not, in general, are not going to be exactly solvable or anything like that. So you need to extract so that's why I wanted to know what property actually they were able to access with their answer. People use these days, these type of methods empirically for many things, okay, even just to go for coffee. But so they use that to study the distribution of galaxies and look at data in the LHC. And so it's a way of manipulating large data sets. But he's trying to access critical behavior, essentially. But for that, he needs to start with some Hamiltonian. So how that Hamiltonian is derived is somebody had to do the more microscopic calculation to derive that Hamiltonian and to know which system is applicable to. But this is not, he's not going to tell you that. So.
Can I ask one more question, because I have to go, and so if I could ask a question. I see that there are questions in the chat, but I assume but I really have to go now. So let me just understand something. So very basic about your talk yesterday. So I just watched it yesterday night. So you do this Monte Carlo, and then if I understand correctly, you could compute many quantities like free energy, correlation functions, and so on. And you chose to compute this effective dimension. And my basic question is, why is this quantity better than other quantities? And the related question would be, you have this distance between configurations. And I guess that will work probably well when the order parameter that distinguishes the transition is very simple and well identified by counting who is up and who is down and things like this. As soon as you will have more complicated topological order parameters, this distance, I guess, could be a disaster. So can you address the two questions a little bit, maybe merging them?
Yeah. I mean, we study one case, right, of topological transition, right, this BKT. So, and I think, yeah, I think the advantage of this method is that when you don't know anything about, let's say, the order parameter that describe your system, and this can be non-trivial, okay? There are examples, like in different contexts, that this is a non-trivial task. Okay, so this is one, I think there's one advantage. The second advantage is when you can like probe transitions that is very complicated to probe otherwise. Like, for example, certain transitions can be probed with entanglement, but the entanglement sometimes is difficult to measure in experiments. And so I would say this is for me, this is the two, in terms of practical terms, this is the two advantage of the method, okay? So, and this is also related to this question that Eduardo asked me, if this quantity can capture multi-body correlations. Okay?
So just for an expert, so if you were to probe like free energy, this BKT and so on, you say it's harder to detect the exponents and well, not exponents, but the value of the temperature and so on. It's harder with free energy than with your dimension.
Exactly. Yeah.
Okay.
So of course there are quantities that you can do, but exactly.
No, very cool. Thank you.
Nathan, you're muted.
Does the person who asked the question on chat want to ask it? I can read it if you want. I don't know who radius S20 is. Okay, I can read. Or you can read it also.
I don't understand how ID and delta R1 was obtained from the dataset. You can have a dataset with up and down photos of the system. Yeah, I think that was exactly, I don't know if this question was answered like before or after, like I mentioned this to Eduardo, but I think, yeah, exactly, compute. Sorry for the noise. So basically, we compute distance at the end, right? So for each point of your data set, that is let's say a vector in a high dimensional space, we compute all the distance from the other neighbors, okay? And then we can access this probability distribution of distance. And from this probability, you can compute this delta 1 and also the ID. So this is the answer. I don't know if I answered your question. Okay. Yeah, for this MMIST, so one thing that I didn't mention is that this intrinsic dimension, this method that we use to compute the intrinsic dimension, in principle it works just for a continuous variable. So for this MMIST can be a problem, this method, to compute the intrinsic dimension. Because whenever you have repetitions, like when you sample, whenever you have repetition of configurations, this method, like two configurations that are equal during my sampling, this method gives problems. Okay, so I cannot apply this method. So for the Ising model, typically we choose like very large system size, so then you don't have this problem. Yeah, the distance is the Euclidean distance. I don't know if it was this that you asked.
Hi, excuse me. You listen?
Yeah.
Yeah, I can listen.
My name is Rodrigo. I'm from Universidade Federal de Juiz de Fora. and I'm working with quantum Monte Carlo and these problems. And my question is, you create a data set or you put some configuration like the minister. You have one configuration, it's a photo or a configuration of the magnetic system. In your case, I think it's 1D quantum Ising model, and you have this data set, and you do measures. You do a measure, and your feature is a classifier that measures the distance using your proposed delta R1, I think. This is like a correlation. I understand this, the correlation between one configuration and another, and you will put these points in a high-dimensional space and measure the distance of some points from another, and you look for other points and then look for this distance, and you will obtain a distribution, like a probability distribution of this feature. Is how the difference of using a fully dense neural network to classify your system of I think that you are creating a classifier, a way to classify your data set.
Yeah, the difference with neural network is that neural network you need to have label data, right, to train your neural network, and here is completely unsupervised. So this is the difference.
Okay, because this is your classifier. You create a classifier that measures the distance from one configuration from another, and so on and so on. And if you have a data set with a classical Monte Carlo, I think this can work too.
Exactly.
Okay.
Yeah, that's the difference. Exactly.
I at this moment I'm working with problems like this, and if you're interested in create some collaboration, I will be happy to take your email and talk about these problems.
Yeah, it'll be nice.
Can you how I need your email because I enter in this talk accidentally, because I'm looking to a presentation. I go to the ICTP site, and it's a very good presentation, I think. Okay, thank you.
Nathan, I think you are unmuted. You are muted, actually.
Yep, sorry, thank you. Are there any other questions from anybody?
Not from me.
Nobody has questions? Okay, so thanks very much, Tiago.
Thank you for you.
Thank you. All right.
Thank you, everybody. Thank you. Yeah, bye-bye.